Greetings, my name is Jerry Rudman. I am one of the professors who is co-advising the student peer teaching project, and I'm going to be presenting lesson 5 today. So let's get right with it, get started. One of the topics that some psychologists have studied is the impact of social network size. Is it positively or negatively correlated with the likelihood of catching a cold or getting the flu or COVID, for example? And you can see one possibility here would be as a person's social network grows and gets more diverse, they could be people at work, at concerts, or they're in large organizations. Others that have very small social networks have a cubicle that they work at and have very few contact with other people. Anyway, as we can see here, as social network diversity increases, the likelihood of a cold would go up. So that's a possibility because as you're out among people, you are exposed to more people who are infected with a cold. The other possibility is social network diversity is negatively correlated with colds. That is to say, people with large social network diversity have a higher immunity to things like colds and influenza because there's some sort of physiological mechanism taking over and helping the person fight off colds as a consequence of their social network diversity. Both cannot be true. So let's see what the research says. First of all, though, before we get into that, I want to do a little bit of background work on correlational research and basics about what are called scatter plots. Now, scatter plots are a visual tool that helps us examine the possible relationship between two variables. The relationship, if there is one, can be easily visioned with the scatter plot. We always plot the data from two variables, x and y. X is always the one that goes on the horizontal of the scatter plot, and y goes on the vertical axis. And each point on the scatter plot represents a score on both the x variable and the y variable. So we can see here that this person's low on both x and y, but somebody over here had a high score on x and a high score on y. Now these dots can move around and be in different positions and take different shapes. A computer program can be used to actually insert what's called the best fit, the sum of least squares line that best represents the relationship between all x and y. And you can see that it's kind of going from bottom left and going up and rising up. That is a sign that this is a positive correlation, not a real high positive correlation, but it is indeed a positive correlation. This line on other scatter plots could be horizontal, indicating a zero correlation, or it could start from up here, upper left, and go down, indicating a negative correlation. Correlational research must be done when the researcher cannot manipulate the independent variable. Some independent variables can't be manipulated. It's just not practical, or it's unethical. In such cases, the researchers can rely on correlational research and rather than true experiments. But that said, the suspected independent variable or causal variable, if we suspect one of them is, like the size of your social network, is always put on the x-axis and may be referred to as the independent variable, even though its high correlation still will not prove that it is a causal variable. Some basic statistics. There's a formula that's used to calculate R. R stands for the coefficient of correlation. It's a simple little number that indicates whether the relationship is positive between x and y or negative, and how strong it is. And there's a computer program, or you can calculate this with a calculator. If you sometimes, you're either now maybe in a statistics course like Psych 10 or Math 10, you definitely will be covering correlation coefficients and how they're calculated. Now, R can vary from minus 1.0, it can't get any more negative than minus 1.0, all the way to plus 1.0, and cannot exceed that. So whatever the value of R, it's always between minus 1 and plus 1. If R is a positive number, say for example, someone says, I have a correlation of plus 0.7, that means that as the values of X increase, so do the values of Y. So here, for example, there's two scores on this person, the person's X score and that person's Y score. Low on both scales. This person over here, high on X and high on Y. If the value is a minus correlation, like minus 0.6, that means that as the value of X goes up, the value of Y goes down. And you would actually see a line that goes this way. And these little, this cluster would be more or less in this direction, going from top left to bottom right. When there's no correlation between X and Y, R will be at or around 0. So here's an imagined study. This isn't actually data from anything that was done, but it's a problem for you to take a look at it and apply what you now know about correlation and scatter plots. Let's say that a researcher asked people how many close friends and acquaintances they had. That's the social network size, or variable X, and how many colds they've had in the last 6 months. And this was plotted. So here's a person that has a very small amount of social network contact and 0 colds. Here's another one, works in a cubicle in some small rural town out in the sticks and sees very few people and has very few colds. Over here we have people who have a large social network, work at large companies, interact with people constantly, and they have more colds. So this is a possible positive correlation. What is the plausible R statistics for this data? Well, if you look this over, we can eliminate E and F right away because you can't have a correlation that's bigger than plus 1.0. So what in the world is 1.2? That's impossible, or more negative than minus 1.0. So those two are out. We also know that this looks like a positive correlation, so D does not make sense, and neither does A. This is a positive correlation. So we are left with these two choices, B or C. What is the correlation? Is it 0.8 plus 0.8 or plus 0.2? Well, based upon my background, I've been teaching statistics for a while, I can tell you this looks like a pretty strong positive correlation, so your best answer is plus 0.8. But this does show you a way that you can, the interaction between the scatter plot and the statistic R, and how you can use them to better understand correlational data. So the big question we have today is a research study that was done in which two different hypotheses were examined. One was that as social network diversity, the more that people have, they're involved actively in clubs, religious organizations, maybe a workplace, they meet a lot of people, the more that happens, the more they are exposed to people who have a cold or a flu or something like that, and they are more likely to get it. So that's one theory. The larger your social network diversity, the more likelihood of getting a cold because of exposure to germs. Now, another alternative hypothesis, which is quite intriguing to me, is this. Social network diversity, actually, the larger it is, the fewer the number of colds. And the theory would be that as people have larger social networks, that actually has a biological or a biochemical effect on them, and they have a higher immune system response. so they're less likely to get colds as a response, as a consequence. So which is true? So we're going to do an interactive now, and I would like you to predict how will the data come out. Now it's time to download and take a look at an article that we have made available for you. You can just open it up. You don't need to print it, but you need to have this article ready to read. Now this is an article by the name of Social Ties and Susceptibility to the Common Cold by Sheldon Cohen and his colleagues. This was published several years ago, and what you're going to be looking at is an actual journal article. It's a professional journal article that was published, and it took advantage of the correlational research design. And there will be questions that you will now be asked, and you can only answer them by looking at this article and getting a little exposure and seeing what a peer-reviewed scientific paper looks like. Okay, now that we've gone through that, I would like to make a couple of closing remarks about correlational research and studies. No matter how large R is, the researcher cannot claim that X causes Y. However, a large R does at least suggest that perhaps X could be the cause of Y. But on the other hand, it could also be that some other variable causes changes in both X and Y. Like we know, for example, that if you took data from cities from across the country, that there's a correlation between the amount of ice cream sold and consumed and the number of drownings that take place in these cities. X does not cause Y, though. Eating ice cream doesn't cause a certain number of people to drown. The true variable is that Z is heat. As the weather warms up, people are more likely to go into ice cream shops, buy ice cream, consume ice cream, and a lot of people also go swimming, and some unfortunately experience drowning. So what's the benefit of correlational research? Well, we can still do research even when it's impossible or unethical to manipulate an independent variable. That's a very important tool. We were not able to study the effect of smoking on lung cancer by doing a controlled true experiment, but correlational data supported it and showed that there is obviously smoking does cause at least some people to develop lung cancer. So that ends today's lesson. I hope that you found it interesting, and we have now left just 3 lessons. Some of you have already completed lesson 6, which is on research on the different types of effective study, and then we have lessons 7 and 8 to go, and we will be done with this whole project. Thank you so much for watching, and have a great day.